Jocelyn presented Neural Basis of Semantic Representations 1, Neural Basis, on Monday, and I'm now going to follow this up with the grounded meaning in sensory motor experience and narrative with the iCub. And I'll just take a moment to also express my appreciation to the iCub project, the Robot Cub project. This is, for those of you who are not familiar with it, it's a European project that was in Framework 6 that was responsible for producing what is today one of the top state-of-the-art humanoid robots that's a real cornerstone of cognitive systems research in Europe. And so we're happy to be part of that adventure that's been going on for about 10 years. So we can ask the question, how can a robot make meaning? And I'm going to try to convince you that the answer to that question is that a robot can make meaning through organizing its own experience based on narrative structure that is provided by humans. And this work is inspired by Jerome Bruner. If you don't know Jerome Bruner, I would highly recommend reading the book called Acts of Meaning. He was one of the pioneers in the development of cognitive science in the 60s. It's an excellent book. So our philosophy, which I think is very coherent with that of the Brian's.
How can I help you?
Our philosophy, which is coherent with that of the brains, minds, and machines, is to understand by creating, so to try to build systems. And we're inspired by this quote from Richard Feynman, a Caltech physicist who had the Nobel Prize in Physics. What I cannot create, I do not understand. And so we're going to adopt this principle in this three-way interaction between cognitive neuroscience, both that we perform ourselves in our own laboratory, as Jocelyn indicated, and cognitive development, feeding into neural network modeling, and then both of these feeding into implementation of these neural systems in robots to interact with humans. So the idea is that we test our neural networks with robots to interact with humans. And the kind of this thing was supposed to not go, so you can turn the sound back on. So the kind of behavior that we're interested in, the kind of thing that we're trying to model that comes from cognitive development, this is a film from Felix Warneken, who's a colleague of yours now at Harvard University, who was a postdoc with Mike Tomasello at the time that this film was made. This is a 2-year-old infant who has seen 1 or 2 times for about 30 seconds this game that they're playing with this double tube. And so after observing very briefly, he's now able to participate in this game. And so this is a cooperative task in that the goal is to drop this little cube down the tube into the can. It makes a funny noise, and so you have to do this with 2 people. The kid's not, his arm span isn't long enough to launch it and catch it at the same time. Now at this point, you see in the lower left, Felix has actually extracted himself from the interaction, and you see the earnestness that this child has. He's trying to get Felix to interact. So this is indicating that cooperation is not just knowing what to do, it's actively wanting to engage the other in the interaction. So this is the kind of behavior that we're interested in capturing. So I'm going to start off with usage-based language learning inspired by Tomasello. So we're going to talk about a model of grammatical construction learning, grammatical constructions as form-to-meaning mappings. And then we'll extend that to shared plans and notions of embodied meaning. And the idea is that we're always unsatisfied with the representations of meaning that we have. And so even with this embodied meaning, there's still something missing, the evolution of meaning over time. And so this is where narrative structure comes in with Bruner. So we're going to talk about narrative constructions as an extension of the notion of grammatical construction and learning narrative structure. So that's kind of the organization. So usage-based language, what is language? One way to think of language is that meaning in language comes from use. Meaning is use. And the structure, the grammatical structure of language emerges from use. So in this context, we can say what would be the neural bases for learning these grammatical constructions that are form to meaning mappings. And so we look to the brain, and primate neuroanatomy is rich and profound, but there are two, I would say there are two fundamental properties of the primate brain that we can concentrate on. The one is the density and the richness of local recurrent connections in cortical circuits. So cortex projects to distant regions that you can see in beautiful DTI figures, but the vast majority of cortical connections are local recurrent connections. And the second major property of the primate brain is the massive projection of the cortex, the neocortex, onto the striatum, the input nucleus of the basal ganglia. So if we're looking for a learning mechanism, we can say that recurrent connections in cortex generate high-dimensional representations of inputs in previous states, and then these high-dimensional representations are projected onto the striatum, where modifiable cortico-striatal synapses read out the required representation. And this leads into the third major characteristic of the primate cortex, if you will, which is the massive dopaminergic projection into the striatum, precisely where these cortical inputs come into the striatum. So we really have a system for learning. And over the last 20 years, we've been developing this notion that the cortex is a recurrent network that we now refer to as a reservoir that projects to the readout where modifiable connections can read out the desired result. And the idea is that in this high-dimensional representation, essentially any projection of the input that you're interested in will be present, and then you can read that out with a linear regression. So this is the kind of thing that I think could be interesting to compare with these deep learning methods. So in the 80s and 90s, there was a furor of activity analyzing this corticostriatal system, noticing that there were parallel corticostriatal loops for the motor system, ocular motor system, more affective related systems. So these kind of dedicated corticostriatal, nigro, thalamocortical loops. And we recently suggested that there's probably a corticostriatal language circuit that can be added to this. And then this is just a plug for a recent paper that we had that just came out last week in PLOS Computational Biology, where we're really doing a detailed analysis between cortical neurodynamics and these reservoir neurodynamics in a complex cognitive task that if you're interested in, that would be a paper you might like to see. So now we're going to use this system to do some learning. And the learning is where we have a kind of a simplified, pragmatic view of grammatical constructions as form to meaning mappings. So this is a typical problem that we would face. We have two different kind of sentences. The dog gave the elephant to the monkey, and the elephant was given to the monkey by the dog, that both, they have different surface forms, but they correspond to the same predicate argument meaning. And so you could ask the question, how can a learning system make this distinction? And so we see that there is a cue, which is these grammatical function words, these closed class words that appear in a different pattern in these two grammatical constructions. So this was suggested by Bates and McQuinney that these grammatical function words can be among the cues that can be used to distinguish these different sentence types. So we're now going to use these grammatical function words as cues for a reservoir system to be able to learn language. And so the idea is for sentence comprehension, we'll take an input sentence and the words, in particular these closed class words, these grammatical function words, will be inputs, sequentially input into the reservoir in the order that they arrive. And the reservoir, which I forget to say, has this particular characteristic that in order to allow the dynamics of the recurrent network to flow over time, we do not modify the recurrent connections in the reservoir. So those are fixed from the outset, and they provide this high-dimensional representation, and then we can read out the response with modifiable, learnable connections. So here, we're trying to represent the meaning of sentences in terms of assignment of each semantic word or open class word, the nouns and verbs, as to the role that they play, the semantic role that they play in the sentence. So here in this sentence, John was hit by Mary. John is it's not the predicate, it's not the agent, it's the object of the first of the first event. The second open class word hit is the predicate, and the third open class word Mary is the agent. So basically we have a corpus of sentence representations and these meaning representations in terms of predicate, agent, object, and recipient, and we're learning the mapping between different sentence forms and this predicate, agent, object, recipient representation of meaning. And what's interesting about this kind of system is that it operates in real time. So we can, if we observe the activity in these readout neurons over time, as this sentence is being presented, the dog chased the cat that bit the boy, and we're looking at the responses for the third open class word, we see that the model is making probabilistic choices over time, and these choices change as different words come into the sentence. And so we see that it's decided right from the outset that this word is the object of the first verb, but it has to wait until this verb appears, bit, before it knows whether it's the agent or not of the second verb. So this is interesting because this model allows us to explain electrophysiological properties like the P600, for example, that occurs when people encounter a word that was unexpected. And also this model can generalize to new grammatical constructions. So are we at 11 minutes? Yeah, okay. So we can do the same kind of system now going in the opposite direction for sentence production. So now we're going to provide meaning inputs to the model and get these activation of closed class elements in the sentence for sentence production. So it's basically flipping the problem around, giving a meaning as input, getting the sentence as output. So we can now insert these sentence production and sentence comprehension models into a robotic kind of system. So we've been doing this for a number of years, and the idea is that we're going to generate a mental model kind of corresponding to these video representations that were talked about in one of the previous talks, a mental model of what's happening. And so if you watch, for example, if I do something like this, then you could say, Peter gave the pointer to John, but you could also say John has the pointer. So this event can be construed in different ways. It can be construed in terms of the force that produces it or the result that occurs. So we can talk about mental models that have these force result representations, but then we can use attention or discourse in order to interrogate the system. Are you interested about the force? Like, do you want to say, what did you do? Or are you interested in the result? What happened? So we can build a system where we're going to tell the robot to do something. It will execute the action. That action can be construed in terms of a force or a result. And then we can ask the robot a question which will determine whether or not you're interested in the force component or the result component. And then the robot will generate a meaning. And then that meaning will go to the sentence production model, and the robot will answer the question. And so here you're going to see an example of that. So you're going to hear Anne-Laure Méliès tell the robot to do something. And the sentences that she's using is kind of grammatically complex because those are more fun for us. So the robot's going to perform the action. Then she's going to ask several questions. And these questions will construe as to whether the robot should answer about what it did or what was the result. So just try to hang on and pay attention.
Before you push the croco on the right, point to the cube.
I have understood. Before you push the croco on the right, point to the cube. Is it okay?
It's right.
Point cube, push croco right. I will do the actions. Do you have any questions?
Yes. What did you do?
I pointed the cube.
And then? What happened?
The croco moved on the right.
How did that happen?
The croco has been pushed by me on the right.
So I hope you could kind of follow along and see that there was a sentence that involved two actions. The robot understood how to use the word before correctly to inverse the order of the actions, performs them, and then answered some questions about what it did versus what happened. So at this point, we're dealing with meaning at a level of single or maybe double events in the in a sentence, and we were interested in extending that to more extended meaning over time. And so we're inspired by the work of Tomasello and his colleagues with shared plans, like the child that I showed you who was doing this joint activity with Felix. And so we kind of analyzed this target article that was in Behavioral and Brain Sciences and said, if we could build a system that could do cooperative activity if it had these properties, if it could perceive state, if it could perceive actions as state changes, so it could do action recognition in terms of state changes, it could distinguish self and other in order to know who's doing what in the shared plan, detect emotional responses in terms of is this good or bad, and then to encode sequences of this kind of elements in some kind of a temporal structure like the autobiographical memory that Tony Prescott talked about yesterday. And so we could build this kind of system based on an autobiographical memory where we're encoding episodes and then doing kind of consolidation to extract semantic concepts. So the autobiographical memory accumulates experience actually in an SQL database, just encoding exactly what does the robot see, what does the person say, what does the robot do, and then doing kind of a consolidation where it's doing data mining in its own experience, looking for regularities, like are there words that co-occur with spatial locations? Are there words that co-occur with state changes that can be associated with action names? And then also storing in this temporal organization of the autobiographical memory, we can store, based on this previously learned actions and names, we can now store sequences of actions that make up shared plans. And so I'm going to show an example here of a shared plan.
What am I going to learn?
So Maxime is going to be telling the robot to put some objects on this musical table into his reach, then he can take them and put them in the exact location to make like a DJ music. So this is a shared music game.
Shared plan.
Okay, I am ready. All in one or action by action?
Action by action.
What will be the shared plan?
You and I play music with the cross and the circle.
I have understood that I, the iCub, and you, the human, will play music with the cross and the circle. Is it good?
Yes.
What is next?
You put the cross to the left.
I have to put the cross to the left. What is next?
I put the cross to the east. Done.
What is next?
So in the interest of time, I'm going to cut this off. So he's basically going to show action by action what to do, and then this action sequence with roles attributed to one or the other is then like a macro that can be immediately used.
You and I play music with the eraser and the cross.
I have understood that I, the iCub, and you, the human, will play music with the eraser and the cross. Is it good?
Yes.
I have to put the eraser to the left.
So there's a kind of argument substitution where he
You
learned.
have to put the eraser to the east. I have to put the cross to the left.
He learned, the iCub learned this task with two objects, and now he can perform it with two different objects. So it's a kind of generalization over the arguments.
You have to put the cross to the south. easy, it was fun.
Okay, so we were satisfied to a certain extent with this kind of development, but there's still something missing. That is, the reservoir model can capture the principles of the Cortico-Striatal system and model semantic role assignment. The autobiographical memory can encode action, preconditions and postconditions and shared plans, but there's still no representation of meaning in a deep sense. And so we can ask, again, the question, how does the brain represent meaning? And Jocelyn referred to the convergence-divergence zone model of Tomasello. So imagine that I'm playing rock, scissors, paper, and every time that I'm doing these things, I'm getting a visual input, I'm getting a motor proprioceptive input, I'm getting input from the auditory system, naming this action, and so these different somatosensory, proprioceptive, visual, auditory, and motor representations converge in a higher order representation, and then if I say the word scissors, I'll have this convergent activity, and then divergent activity will reactivate these other representations. So, for example, I should be able to form a mental image of my hand in the scissors configuration. So, and so this is the fMRI data that we saw, again, allows us to answer the question, how does the brain represent meaning? By reactivating memories of its own experience. So when you see a picture like this or you read a sentence, you actually activate anterior pole, temporal pole, medial temporal gyrus, motor integration related activity in the parietal cortex. So it's as if you're, in a certain sense, reliving your own experience of this kind of activity. So we could do this in the iCub. So we have the iCub. It's got arm proprioception, it's got head proprioception, it's got vision, and it can have speech input. So when it's doing something like rock, scissors, paper, it's getting these multimodal representations that can be encoded in here in Cajonen-like self-organizing maps. And then each of these map representations can go into a higher order map. So then once these convergent associative representations that link together the word scissors with the proprioceptive joint angles of this and the visual scene of this, when the robot just hears the word scissors, it will actually re-evoke a mental image of this configuration. It could also re-evoke the proprioceptive signal to make that action. So here we have for the first time a really grounded representation of meaning. But so now we want to go beyond that and extend this in time to the notion of narrative constructions. So Bruner, and so grammatical constructions are limited to single sentences. Narrative constructions will extend over multiple sentences and multiple events. And so narrative establishes context over time. It allows the structuring of the content of autobiographical memory, and it creates meaning by introducing unseen relations. So just a couple quotes from Bruner. Logical thought is not the only mode of thought. There is a different form of thought that goes into the construction not of logical or inductive arguments, but of stories or narratives. So this is kind of a groundbreaking way of thinking about things, that there are multiple thought systems. The narrative construction of reality. Narrative is a form not only of representing, but of constituting reality. So we can say that the narrative construction is analogous to the grammatical construction. So it's a mapping of linguistic form to semantic meaning, but at the multiple sentence level. And so we'll extend this notion of grammatical function words like to and by to discourse narrative function words like because and so and then. So we've got our model of the neural networks for comprehension and production, and they're now going to integrate with the autobiographical memory, but adding in an additional narrative context component in addition to the inputs that we were using before. So it's basically sentence comprehension and production plus narrative context. And so I'm just going to show you an example. Here's the iCub living a story. It's trying to grasp this Winnie. It has a goal it's trying to grasp. It fails. So now to trying to find, do I have another way to achieve this goal?
Give me the winning, please.
So now the goal has been fulfilled. Now we're going to look at the iCub. It tries to tell the story itself, but the story makes no sense. So then we have this kind of human enculturation where Gregoire is going to tell the robot, here's how you should tell the story.
I wanted to get the winning. Yes. But I failed to grasp it.
So he's using words like but.
Yes. Because it laid out of reach.
And because, so making links between events that occur. So after this learning, now the robot, he's going to go through the same kind of thing with me now, but instead of trying to get the Winnie, he's trying to get the bottle, and instead of with Gregoire, it's with me. So now he has this new experience that fits pretty well with the template that he's learned, and so now he can tell the story himself in a reasonable way.
I wanted to get the bottle, but I failed to grasp it, because it laid out of reach. So I found a different action. If I could ask Peter to give it to me, then Peter would give it to me. So I asked Peter to give it to me, and Peter gave it to me. Now I have the bottle.
So the idea here is that we are going to, within the autobiographical memory, everything that the robot does during living his life gets encoded. Through that autobiographical memory, we can automatically create a kind of semantic representation of what happened, but that's not enough. Some of the causal relations will be missing. So then the human narrator is going to provide additional inputs that include these causal links. And so we can make meaning in different ways. The first way is just understanding these kind of narratives. The second that's really interesting is learning the causal role of intentions. So for example, in the narrative, the can appear something like, you gave me the giraffe because I wanted it. And when the robot hears that, he can make the link. It knows what because means because of causal relations between these force-result verbs that it learned earlier. So by saying, your mental state was the cause for some action that I performed, narrative is imposing and adding meaning to the experience. And then there's also this notion of metaphorical transfer where you can actually plug in, instead of physical objects, the robot can want to understand math instead of having the giraffe. So it could hear a story about more abstract things and make the same kind of causal relations between that it knew for physical objects and now extend them to more abstract things. So in conclusion, we're considering that like all social activity, narrative can be considered as narrative is constructed as a form of joint action where there's behavior that occurs and narrative that's provided by caretakers. Narrative constructions are learned as normative structures for organizing and communicating events. They impose meaning like these causal relations on events. And the notion of grammatical construction that we've developed as a form of form-to-meaning mapping can be naturally extended to narrative constructions, and this can be built up in the framework of this Cortico-Striatal reservoir system. So I just want to briefly thank the people who contributed to this work, so briefly that that's it, and then thank you and ask questions if you have any.